As we start this evening's NOAA Planet Stewards June webinar, we have some information to provide before we begin the actual presentations. First of all, tonight's broadcast is being recorded and everyone will receive a link to the video archive. Now, if you don't receive a link within 1 week, then please email me with the subject, request link, May 2018 webinar. A video archive and all slides that are presented tonight and of all previous broadcasts going back to 2013 are available on the NOAA Planet Stewards Google website. And if you can't access it, please send an automatic access request through Google or through email to me with the subject request access to PSEP Google site. As a note, all attendee microphones will be muted during the broadcast. If you'd like to ask Dr. Bricker, Ms. Harrison, or myself a question or provide a comment during the course of the broadcast, please type it into your GoToWebinar panel. In addition, during tonight's broadcast, if you registered, you're going to receive an email with a link to a post-webinar poll. Now, please go to your email right after the webinar, answer the poll. It will take about a minute, maybe a minute and a half tops. Really, we look at all of the responses and they do help us in terms of developing and evolving the content for these presentations. For those of you who are remaining on for the full period of the hour, you will be receiving a certificate of attendance acknowledging your participation with 1 hour of contact with professional development. And again, before we begin, I have some announcements about some NOAA Planet Stewards sponsored workshops that will be held all around the United States this coming summer. First of all, we have one which will be taking place in Flagstaff, Arizona, in partnership with Flagstaff United and STEM City in Flagstaff, Arizona. The Changing Southwest Environment, Trends and Challenges. This is going to be from June 11th through 13th. They're going to be offering increased information on subjects relating to the Southwest environment and environmental impacts that are occurring, educational resources. There's going to be hands-on instructional unit development, and the focus is really going to be on understanding complex systems of the Southwest and applying systems thinking to regional issues of extreme weather, fire, drought, flooding, and ecosystem dynamics. In June 25th through 28th, there's actually going to be a 4-day workshop that's going to be down in the Houston-Galveston area. It's going to be held in Lamarck, Texas. The focus is on environmental impacts to the Gulf Coast. What do we know? What can we do? We're going to be focusing on climate change and ocean acidification and the impacts to the Gulf of Mexico. And there are going to be a lot of hands-on activities and also some field trips too. This is particularly recommended for formal and informal educators of middle and high school students. And you see there is a link there where you can also go and register. For some of these workshops, space is limited, so please pay attention to that. Finally, there's going to be another workshop and 1-day long symposium, Resilience, Education, and Action, Our Place in a Changing World. It's going to be focusing on citizen science, developing quantifiable research projects, active STEM experiences, and connecting with diverse audiences through cultural practice. The 1-day symposium will be in the Honolulu Convention Center in Oahu, Hawaii, and there's also going to be a special 2-day pre-symposium held at Moku'oloi, or Coconut Island, also in the vicinity of Oahu, Hawaii. And it's going to only be open for 40 educators, the pre-symposium, and it is available for special PD3 credit opportunities for Hawaii educators. And for more information and to register, there is a link there at the bottom. And with that, I'd actually like to turn it over to our first presenter, and I'd like to introduce them to you formally. Hi, Suzanne. So your mic is hot and you...
Okay. I just shared my screen. Okay. Hi, everyone. Thanks for joining us this evening. My name is Suzanne Bricker, as Bruce has said, and I want to thank Bruce and also Molly for allowing me to share my work with you. The first thing I'd like to do is tell you what the word eutrophication means. And the origin of that word means well fed, and it means basically nutrient pollution. So what I want to tell you about today is the research that we've been doing since the early 1990s to look at the status of eutrophication in coastal water bodies of the United States and elsewhere, and also, intriguingly, what shellfish aquaculture, and if I forget to say it later, I want to say that we're focused on shellfish aquaculture, but we also include wild shellfish. So if I forget to say that later, I'd like to say that now. And the big question, can shellfish improve water quality? Before I begin, I'd like to acknowledge my co-authors whose names you see here. I've been working with them for quite a long time, and it is not only a multidisciplinary team of people, but also an international team. And it's been really fun to work with them because I've learned so much from my colleagues. And what I'd like to do is show you a picture of some of them here. This isn't all of them, and as you can see, some of them have been added on. If you look in the first row here, you'll see that we actually had a representative from the Bayou who attended most of our conferences. So I am especially grateful to them for allowing me to be a mouthpiece, but the reason for showing this is to emphasize that this is not only my work, but rather the work of all these and more people that I will be telling you about today. So, starting out with this, what is eutrophication and is it a problem? And as I've already said, nutrient pollution is basically what that means. When we have excess nutrients coming into the coastal waters, that immediately causes algal blooms. When those algal blooms die, they decay and they use up oxygen in that process. They also cause the water to be cloudy, and so that kills off seagrasses, which are important habitat nursery areas for some kinds of fish. And in fact, what we've discovered is that 65% of US estuaries have moderate to high eutrophication or nutrient-related impacts. And so in this figure, in the bottom, what you see is on the left-hand side of the panel, the kind of water body we'd like to see with lots of oxygen and a lot of seagrass, some phytoplankton, which is microscopic algae in the water. That's food for fish and oysters. As you move from the left to the right, that is representative of increasing nutrient inputs. And what you see on the very right-hand side is a situation that we would rather not see, which is high-level impacts from nutrients, which include your losses of seagrass because of the water cloudiness, different kinds of algae that can cause illnesses and kill fish, low dissolved oxygen, which kills fish. So these indicators that you see, these 5: submerged aquatic vegetation, chlorophyll A, nuisance and toxic blooms, macroalgae, and dissolved oxygen, are the indicators that we use in order to evaluate what the level of the nutrient pollution or eutrophication is in water bodies. So going on, so what about nutrients? What's the problem? Well, as I mentioned, it's too much of a good thing. It's a little bit like when we overeat. It is a nitrogen, which is the nutrient that we will focus on, because that's the one that is most problematic in waters that have salt in them. So the marine and nearshore coastal marine waters. That's a building block for all kinds of life. However, when you have too much, it causes problems. And those include algal blooms, loss of seagrasses because of the cloudiness, as I've mentioned, and low dissolved oxygen, which kills fish. And so I thought it might be useful to see what does it really look like in real life and where does it happen. And so here is a panel of 4 photos. You see a very heavy algal bloom in Potomac River, Maryland, and that's probably 3/4 of an inch or an inch thick. In Corsica River, Maryland, you have fish kills from low dissolved oxygen. In Florida Bay, colonizing algae are killing out the seagrasses, and you can see the turbidity in the water is cloudy. And then Caloosahatchee Bay, Florida. Now, you may have heard of red tides, which can cause respiratory illnesses, and also they're considered harmful algal blooms. They can cause other kinds of like amnesia problems, diuretic illnesses. And what you see here is not a red tide bloom. They don't have to be red, but they still can be harmful. In this next slide, you'll see other pictures, and in the left-hand top picture, in Venice, Italy, they have problems with colonizing algae on their steps there. In Washington State and Hood Canal, Washington, you've got problems. And in Qingdao, China, they had these massive algal blooms when the Olympics were there several years ago. And I think the lower right-hand picture really is very compelling. So this is what it looks like. Part of the reason for showing you these photographs is to say, in the United States is not the only place that these problems occur. They actually occur all over the world. And some of the colleagues that I have worked in these different places. And so we try to share information about how to evaluate it and also what to do about it. So where do nutrients come from? There are different sources, and they're basically divided into 2 kinds. One is a point source, and that's shown on this slide. Wastewater treatment plants, and I'd like to talk a little bit about that. While they do remove many nutrients in their effluent or their discharge, there still are levels of nutrients that are discharged to coastal waters. They actually do a good job, but they don't remove 100%. You also have animal feeding operations, and then in this picture you see a pipe, which is very typical of a point source. Non-point sources are from septic systems, from lawn runoff, from urban runoff, and these other things you see here. When you drive your car, you're contributing to atmospheric deposition of nutrients. So there are many ways to reduce nutrients. The point sources are the easier one between point and non-point sources, and you can also see from the previous slide here that point sources are smaller than non-point sources. Part of the reason for that is that we've been successful in reducing nutrient discharges from point sources, and now we have the challenge of addressing the non-point sources. And just as an example, in Long Island Sound, which I'll tell you about in a little bit, that's my case study that I would like to talk about. Point sources are 25% of nitrogen input, and non-point sources are 75%. In Great Bay Piscataqua Estuary, which is up in New Hampshire and partly in Maine, point sources account for 32% and non-point for 68%. And in the Choptank River Estuary here in Chesapeake Bay region, point sources contribute 10% and non-point sources 90%. So it does depend where you are. In other words, if you're in an urban area or an agricultural area, you may see more nutrients in an agricultural setting because you have more runoff than in a city setting. But the other thing to note is that eutrophication is a natural process, but because of human activities in the watershed, we've accelerated that process to many times the natural rate of eutrophication. So we have 65% of US estuaries that have moderate to high level nutrient impacts. We know that nutrient management measures have worked, as I said, especially for the point sources. Non-point sources have also, but they're more difficult just because there's not one point of entry that you can address. So the discussion has been how to be more effective at nutrient management. And so one of the things that has been discussed is this idea that bivalve shellfish, so the ones that filter with siphons, such as oysters and clams and mussels, that they may actually help to remove nutrients. And so the other thing to note is, well, let me go to the next slide, and what I call the mighty bivalve, because of what they are able to do. We call this bioextraction of nutrients. And through their filtering activities, these bivalve shellfish remove particulates and detritus from the water, and by doing so, they actually remove nutrients from the water. So here we see several different kinds of shellfish. One of the most striking shellfish I've ever seen is this geoduck clam, which occurs in the Pacific Northwest. And then we have clams and mussels of different kinds. And then the star of our show, the eastern oyster, or Chrysostrea virginica. Now, I think that all of you have probably heard that oyster levels in Chesapeake Bay, certainly, but it's true worldwide, have declined to about 1% of historical levels. And the reason that that's not good, besides the fact that there aren't as many to eat, is that, for example, in Chesapeake Bay, 100 years ago, there was a huge population of oysters that was able to filter the whole volume of Chesapeake Bay in 1 week. The populations we have now, it takes more than a year to filter that same amount of water. And so our focus is to look at the eastern oyster and, as a representative of shellfish, to see about how they might contribute to nutrient remediation or nutrient removal in our water bodies. So why would we consider doing that besides what I've said? Well, eutrophication is a problem in the US and also globally. As I've said, point source controls have been successful. The other thing to know about that is when the technologies increase, they become much, much more expensive, so that the economic returns are not beneficial. So that's one reason for looking at alternative measures. Non-point sources are more difficult to control. And as I've said, land-based reductions of nutrients in management measures have been successful, but at this point, they have not shown expected water quality improvements. And so oysters can filter a huge amount, as we've said. And so that's why we wanted to look at, in a robust way, how well they might do to contribute to nutrient management, to nitrogen management in particular. So we designed a study in Long Island Sound, and the questions that we wanted to answer were what the eutrophic condition or the nutrient-related water quality was in that water body in Long Island Sound. And we also know, and part of the reason for choosing that place is that they have a very well-developed oyster aquaculture industry. And in addition to that, we wanted to then look at the value of the ecosystem service. So when I say that, the ecosystem service, that what we're talking about is the benefit that these shellfish provide to the water body. And so the one that we're most focused on here is the cleaning capacity, so their ability to remove nutrients. But there are others. So, for example, shoreline stabilization, improvements of water quality, clarity, and then there are also some cultural services, but none of these did we evaluate. But I just wanted to let you know that nutrient removal is not the only ecosystem service that they provide. The big question is this one in bold. Can shellfish, and in this case oysters, improve water quality? Can they remove nutrients? And then an intriguing corollary to the value of that system is whether in a nutrient credit trading program, which are being set up in many water bodies around the US, would those oyster growers be able to be compensated for the work that the oysters are doing to improve water quality? And so we'll talk a little bit about that also. So here's our study site, Long Island Sound. And the reason for showing you this map is that in these blue dots are places that we have either completed or are doing work in this same framework that I'm about to talk about. And studies have also been conducted in Europe and China. Since I'm going sampling tomorrow in Chesapeake Bay, I wanted to let you know that the overlapping dots here in Chesapeake Bay is an ongoing project that maybe Bruce would allow me to come and talk about in another time. But we are doing the same kind of work right here in our own backyard. So this is the framework, the bioextraction framework, which is in Long Island Sound, what we used with that multidisciplinary team. And I just have to tell you, again, that I learned a lot from the people whose disciplines were different than mine. And the results that I will show you will seem like, oh, that's really easy. And it wasn't, but it was really gratifying. So what you see here is that we had field measurements. We used both system scale eutrophication models. We use also a system scale ecological model. We use a local scale farm production model. We use an economic model, catchment models, which tell us how much nutrient is running from the watershed into the water. And we also did growth measurements in the lab. So in addition to being multidisciplinary, it had a lot of what I would call moving parts within the project. The ones in red are the ones I'll talk about. The first thing that I want to tell you about is the eutrophication assessment, which is on the left-hand side, this ASSET. Stands for Assessment of Estuarine Eutrophication Status. So we're looking at the eutrophication status in Long Island Sound, which is an estuary, which, just to define that, an estuary is where seawater and freshwater mix. Then on the upper right-hand side, that's our third component, the economic model. And in the middle, I'll tell you about our system scale modeling with primarily with the eco-wind model. So this is a picture, again, of Long Island Sound, a map. And you'll see it's shared by Connecticut and New York. Here are some quick facts at the bottom. It's about 3,200 square kilometers. Residence time is fairly long. It has, as you would imagine, a highly developed watershed. It includes Hartford, Connecticut, and also New York in that region. What you'll see in the map are, in red, we blocked out sections of Long Island Sound, and even though it's shared by Connecticut and New York, we were only able to get information enough for Connecticut. So when I say Long Island Sound, I'm actually referring to the Connecticut side of Long Island Sound, which is what we studied. So I draw your attention to the very western portion, which is called the Narrows, and the very eastern section, which is called Eastern. Because this next slide shows data for bottom water dissolved oxygen, and what you see is this for January through December for the Narrows on the left-hand side, and for the eastern zone on the right-hand side. So the first thing to draw your attention to is that this is in milligrams per liter. You can see the scale on the left-hand side goes from 0. Now, 0 milligrams per liter is considered anoxic. That will kill fish and other organisms that need oxygen to survive. It goes up to 16 milligrams per liter. And what you see in that red line, dashed line, is the 4 milligrams per liter line. At 4 milligrams per liter, that concentration is low enough that organisms that can move will move out of the area because it's stressful to them, biologically stressful. So there are two other observations to make. In the eastern, the data on the eastern side show no levels that are even close to 4 milligrams per liter, which means that that water is fine for fish to live in and oysters. In the Narrows, you'll see that in the summertime, there is every single year a drop of dissolved oxygen below 4 milligrams per liter and almost down to 0. So what this tells us is that we do have some nutrient-related problems in Long Island Sound. Okay, so that data and other data, including measures of how much microscopic algae, the phytoplankton, how much is in the water. We call that chlorophyll A. It's an indicator of how much algae is in the water. So that's the measure that we use. So we use dissolved oxygen, we use chlorophyll A. We look at the occurrence of nuisance blooms and toxic blooms of algae. We also look at the occurrence of blooms of macroalgae, such as sea lettuce, which it looks like lettuce. It floats around in the water, and you may have seen it if you're boating or if you're on the beach. And then again, dissolved oxygen. And here's this picture again, from no or low impact on the left-hand side to high impact from nutrients on the right-hand side. In our eutrophication assessment, we use 3 indices. What we're trying to do is put together a picture of what's the primary cause, so nutrient inputs from the water body, and also how fast the water moves through, what the condition is based on these 5 indicators, and then also our final thing is what will happen next. What will happen next based on what kind of management programs are being implemented, what kind of population changes are expected in the future. That's the least robust of our indicators. or our indices. But so let's go forward, and I want to summarize the results for you of the assessment we did in Long Island Sound. So this is the influencing factors. We use two things to look at that index. We look at nutrient loads and we look at residence time. And so at the bottom, you'll see these colored circles and then what that indicates with respect to the rating. So for example, nutrient loads are considered moderate. They are 50,000 metric tons of nitrogen that are discharged per year into Long Island Sound. And here are again some photographs of where that comes from, point and non-point sources. Because the residence time is also moderate, so 2 to 3 months is, with that amount of nutrient coming into the system, that is enough time for algal blooms to develop. And once that happens and then they die off and sink to the bottom, then that's when you begin to have problems. So the influencing factors together, the nutrient loads and residence time, give the influencing factors a moderate rating. The condition rating overall is considered moderate high. Now, for these 5 different indicators, we look at the concentration, we look at spatial coverage, and we look at frequency of occurrence. We look at that over an annual period, as I showed with the data in the dissolved oxygen. And for example, using dissolved oxygen, you'll see that's the 3rd one down. That's in yellow because of the biologically stressful concentrations occur over a high area every year. You'll see that macroalgae, losses of seagrasses, and nuisance and toxic algal blooms have either a low or no indication of problems. But chlorophyll A is high. It's red, which means it's a high impact because the concentrations are high, and those high concentrations occur over a large area every single year. So those indicators taken together give the condition, the eutrophic condition, a rating of moderate high. So then we go to the future outlook, and actually that's a little bit more optimistic. What you see here in green is that nutrient loads are expected to decrease in the future. Because the residence time will remain the same, it's considered moderate, but the two together provide a more optimistic view, which is that in the future, as nutrient loads decrease, that there will be some improvement. And if you look at the picture on the bottom, you'll see that there are 2 ways as you move from left to right of a water body to go. Either it can worsen or it can improve. And our future outlook for Long Island Sound is that it will improve. Now, it improves, the green color indicates that it improves on a slower level than it could, but still it is improving. So that's optimistic. So the other thing we do with these 3 indicators, or these 3 indices, the influencing factors, condition, and future outlook, is to roll them together to provide one rating for each system so that we can compare one to the other. In our national study, we looked at 141 systems. So for Long Island Sound, that rating would be considered poor. But this is an improvement from bad, which is what it was considered in the early 2000s. These data are for 2008 to 2012. So we can see optimistically these things are improving, which is really nice to know. So the next thing is to consider then, well, how might oysters be useful, or how can they help? And the way that we are trying to figure that out in this study was to use we used models to look at the bioextraction of nutrients. And our model is called EcoWin. It is a system scale model, so it looks at the entire, and if you remember when I say entire, what I actually mean is Connecticut side of Long Island Sound. And so what did we want that model to do? We wanted it to be able to estimate nitrogen removal by oyster aquaculture within Long Island Sound of Connecticut. So we wanted to apply a model that would grow oysters in order to estimate that nitrogen removal by all the farms that are there. Then what we did was we wanted to compare that removed amount to the incoming nutrients, which remember is 50,000 metric tons per year, and then estimate the economic or the dollar value, looking at how much is that worth? So we needed an oyster growth model for Long Island Sound, which we did not have. We took the model EcoWin, which had been developed for estuaries in Europe, and what we did was developed an oyster growth model that we could then integrate and into that model for growing Chrysostrea virginica, the eastern oyster, rather than Pacific oyster, which was the original model species. And what you see here are in the red circle, which are the diamonds that are to the very left-hand side, and what you see here is time in days, and you see shell length. So you have one single oyster growing over 2 or 3 years, and you'll see that that we used old data as well. And so we developed this growth curve for the model in order to simulate the production of oysters and also nutrient removal by aquaculture. So here's the way the model looks, and in the background you can see the input, and in the foreground you can see what the model automatically creates. It's a mass balance. And so I show you this to say that the phytoplankton and detritus, so the particulates in the water, are filtered out they're eaten by the oysters. Some of that goes into tissue and shell growth, and some of it is excreted. So what is assimilated into tissue and shell is no longer available to grow algae or to start the problem of eutrophication. So that's the kind of thing that we were trying to measure. So in this next slide, we use that growth model to, let me back up. So the Long Island Sound, part of what was attractive to us to do this modeling there is that they already had a high-resolution, three-dimensional model called System-Wide Eutrophication Model. The time frame that it operates on the simulation is 1 year, and the focus for that was water circulation and water quality. So it looked at nutrients and dissolved oxygen and salinity and temperature. And in this picture, the blue thin lines are the boxes on one layer of the SWEM model, the system-wide eutrophication model. And it had 10 layers and 230 boxes on one layer. So it had 2,300 boxes that simulate how the water moves back and forward and exchanges from box to box in the sound. What you also see superimposed here are in green the approved aquaculture areas. In the darker blue is conditional, the lighter blue is restricted, and in red is prohibited. So we used those aquaculture areas plus water quality and physical and also legal. For example, we did not want to simulate growth of the oysters and production of oysters in places where they would not be allowed to grow. So what we did was we merged that high resolution model into 42 boxes for our ecological model, which, as you see in this table, has a decadal time. So it has a 10-year time frame of simulation, and that's what we need in order to simulate aquaculture growth and the water quality that's associated with that. And in addition, that time frame is what is important to look at the economics. So what we did was we merged these two models and made it into a model that could push the water around and the substances, and in addition grow the oysters and give the results that we needed to use for the economic analysis. So this next slide shows the output from that system-wide model. And what we're looking at is actually the nutrient removal mass balance. And so what you see for shellfish filtration in the green boxes, so that is in kilograms of carbon units, how much phytoplankton is removed and how much detritus is removed. So how much is filtered out by the oysters. When you look at the box on the right, we have converted those carbon units into nitrogen units. And what you see is that algae and detritus are removed. They have a negative sign in front of them. And excretion, feces, and mortality actually add nitrogen to the water. But the balance of if you remember, what they eat, they assimilate some, and then they excrete some, just like we do, right? And so the mass balance of that is actually a removal of 377 kilograms per year of nitrogen. That's in the current aquaculture acres, 5,250 acres. So one question we also were wondering is, how much could we expand aquaculture in Long Island Sound in the Connecticut side, and at maximum acres, how much nutrient would that remove? And so what we see here is the result of that, 1,337 metric tons per year. So what we did was to compare what their oysters are removing compared to what nutrients are coming in. And what you see here is that 1.3% removal of the incoming nitrogen by current aquaculture, up to a maximum of 2.7% of incoming nitrogen. Now that, I have to tell you, was a little bit disappointing. But what you need to remember is that every little bit helps. That's one thing. The second thing is that the statistic for shellfish and any seafood here in the US is that we import more than 90% of what we consume. So in addition to maybe taking what seems like only a little bit of nitrogen out, you're still producing seafood for people to eat, producing it here domestically and in a sustainable way. And so that's actually really very exciting. So the next question is, and might make you feel better, is how much is that nutrient removal worth? Oh, and one last comment about that. As the nutrient inputs continue to decline, because nutrient management measures are designed to do that. So all the time we're improving our nutrient management so that the 50,000 metric tons of nitrogen now will not be 50,000 metric tons later. We're expecting them to decrease, if you remember from the eutrophication assessment. And what that will mean is that, relatively speaking, the removal by the oysters will at least look or be relatively more important. So, but still, how much is that worth? So the way that we did the analysis for what is the value is by using what we call an avoided cost or a replacement cost method. And what that method assumes is that these shellfish are doing, if you recall, we call it an ecosystem service. So they're actually providing a water cleaning service. If they didn't do that, then some other kind of management or service would have to be used in order to replace the service that they provide. And so the way that we develop an estimate of how much it's worth is by looking at the costs for those other management measures. So for example, how much does it cost a wastewater treatment plant to remove the same amount of nitrogen that all those oysters are removing? And then we assign that value to the removed nitrogen. And so the different management or the alternative management measures that we are using for that estimate are wastewater treatment. And you can see here from this slide, we use the annualized capital and operating and maintenance costs of the load reductions that they provide. We also use costs of agricultural best management practices, such as the cost to implement cover crops on a per acre basis. And then the third one that we used was urban best management practices, and that is using the costs to construct wet ponds, such as the ones that you see along highways and so forth. So those are the three alternative management measures that we use to make our estimates. So our replacement costs or our avoided costs for nitrogen removal in Long Island Sound are shown in this table. And so what I'd like to direct your attention to first is the dollars per kilogram nitrogen removed. So the first three are 8 milligrams per liter under management approach, 5 milligrams and 3 milligrams per liter. If you recall earlier, I said wastewater treatment, as you increase the removal of nitrogen in the waste flow, it becomes more and more expensive. And so actually, that's exactly what you see here. If you have a less stringent kind of removal, it's on for, and you have 8 milligrams of nitrogen per liter coming out of the pipe at the end, the cost to remove the other is $32 per kilogram. Where if you're more stringent up it and lower it to 3 milligrams per liter, it's almost $100 per kilogram. Then the agricultural best management practices, they're the least costly to remove 1 kilogram of nitrogen. And the urban best management practices are the most costly. Some of that is has to do with buying land in order to make those wet ponds and holding ponds in urban areas. But then if you look on the column on the right, the total value in millions of dollars per year for current acres, the range is $8.5 to $230 million per year. So that actually is a fairly significant number. If you use the maximum possible acres for aquaculture, the maximum value increases to $470 million per year. So that is a fairly large number. And the big question is, so what about payment for that service? Those oysters are doing a lot of work that's very valuable. So the question is, will growers be paid for the nitrogen removal service that their oysters are providing? And I would like to say that they will be, but it is at least under discussion. And in a well-developed nutrient credit trading program, that might actually happen. But that has not happened yet. It is being discussed, but it has not happened. However, one very exciting result of the work that I and my colleagues and other people have been doing is that Chesapeake Bay program in December 2016 approved the use of harvested oyster tissue as a nitrogen and phosphorus removal best management practice. And what does that mean? That means that the jurisdictions that are required to remove nitrogen that is being discharged into the water body because they've been evaluated and found to be have undesirable eutrophic conditions, the plan that is made to reduce the nutrient loads can now include harvest of 1 or 2 million oysters. And so that is very, very exciting, and I think answers fairly well the question that we wanted to answer, which is, can shellfish help water quality? The answer here is yes, it can. And in Mashpee, Massachusetts, they're already using harvested oysters for nutrient management. I just read in the newspaper this week that in Maryland freshwater streams, mussels are being restored specifically for water quality improvement. And in Denmark, they also have mussel fields of mussel ropes that are specifically used for nutrient control. So the answer about whether oysters and other shellfish can help improve water quality, the answer is yes. And it's gaining momentum not only here in the United States, but around the world, it's very exciting. And in fact, the first paper ever to come out exploring this concept was done in Sweden and in 2005. And so it's really gratifying to know that that concept is now actually being used to improve water quality. So I just have a couple of additional slides, and the first is in my closing observations that we were using Long Island Sound, which is one of those 65% of U.S. estuaries which have moderate to high level nutrient related impacts in a bad way. So we were using that as an example to say that additional nutrient management is needed, and what we're trying to do is be creative and look at alternative management measures that can complement traditional land-based measures. And oysters and other shellfish are a very promising method. We've used models, and as you could see, it really reduces the financial and the time costs, not to mention environmental and social time costs, or costs of, for example, implementing and trying to figure out whether oysters are useful for nutrient management. So models are extremely useful and have shown us really what we want to see, which is that oyster aquaculture can remove nitrogen inputs. 1.3 to 2.7% of nitrogen inputs in Long Island Sound. The comment I have about that is because it's looking only at aquaculture, that actually it is an underestimate, because the wild harvested oysters, clams, they're also doing the same kind of service. So this 1.3% of current acres is actually probably higher. We also have not included denitrification, which is a bacterially mediated process that removes nitrogen in oyster reefs. So this is very promising, and while we might have been a little disappointed at the low percentage of nitrogen inputs compared to what's coming in, it is an underestimate. The ecosystem service value is quite significant, and the value of the decreased hypoxia, what you see here, shoreline stabilization, those other kinds of ecosystem services aren't even included here. And so I think that we have shown very optimistically what oysters can do and what this kind of a project can highlight. And then finally, you may all be wondering, what can you do to help? One of the things is just to keep it on your mind and be mindful of your personal actions that contribute to nutrient pollution. Oyster gardening and oyster planting with Department of Natural Resources and Chesapeake Bay Foundation, Maryland Sea Grant, that is one thing that can really help. And I learned from Chris Judy, who's the director of the Maryland DNR Shellfish Division, that the Maryland DNR, Maryland Grows Oysters, you can actually hang oysters off your dock. And if that Maryland Grows Oysters is active in your tributary, then you can be signed up by the Maryland DNR. But if it's not, you still can do that same thing via the Chesapeake Bay Foundation. And so if you are interested in doing that, you can look them up online or contact me and I'd be happy to hook you up with the contact information. And Sea Grant has also developed a how-to guide called Oyster Gardening for Restoration and Education that might be of interest. So oyster gardening and oyster planting is one really great way to do that. But you can also build a rain garden at your house, at your church, at your school that will reduce the amount of nutrients that are running off into any tributary. You can ride a bike instead of taking the car. You can reduce your fertilizer use, or, because that's not always practical, be mindful of when you use it. For example, don't put fertilizer out when you know there's going to be a really heavy rain and it might just all wash off anyway. And in any case, join your local riverkeeper or watershed action planning or watershed steward group. These are just a few ideas for how you might be able to personally help nutrient management, and then finally eat more shellfish, and so that you would support your oyster and clam growers, and nutrient removal. So this is my last slide. We've already answered this question. Oysters and other bivalve shellfish can help improve water quality and also provide seafood, and there you see them doing their work. So thanks very much. I'm very happy to be able to share our work with you, and if you have any questions, I would be quite happy to answer them.
Hi, Suzanne. This is Bruce, and I'm back. Thank you so much for that presentation and just taking it away when I got cut off earlier.
Oh, you were cut off? Okay. Hey, I forgot to say, you can try the models yourself. And then there's my address. So anyway, Bruce, did you see any questions on the, or does anybody have questions for me?
Yes, actually, we do have a few questions. So you may want to keep your screen on. Here are a few questions for you.
Okay.
And we'll take just a few, and then we're going to pass it over to Molly, who actually has a presentation on
Great.
some
Okay.
three-dimensional learning resources, all focused on oysters for use in the classroom. So one question is, considering harmful algae doesn't have to be red, how can one tell the difference between harmful algae and benign algae?
That's a very, very good question. The species of algae is what makes them toxic or not toxic. And so there are, so let's talk about for eating oysters and clams and so forth. Health departments in every estuary are looking at whether or not those filter feeders, those bivalve shellfish, are actually taking in algae that are toxic. So they are doing tests of the water. And I'm not sure of the exact test they do, but these things are monitored. And I could give you information about who to contact in NOAA about the exact tests that are done. For example, the Department of Natural Resources has a really nice description in their Eyes on the Bay, the Chesapeake Bay program site, that talks about harmful and nuisance algae. So I'm not sure that answers very well your question, but it's the species of algae is what makes the difference. Some species are toxic and some are not. And then some that aren't toxic, like these, they're called brown tides. The algae is so tiny that it clogs up the filter feeders, siphons, and they die. And so that's also been a problem in the past. So whoever that is, if you would write a note to me, I'd be happy to, if you want to, or you could look just at the Eyes on the Bay site and look under their nuisance and toxic bloom. They have a link to that.
Thanks, Suzanne. I'm going to ask one more question to you, and then we're quickly going to take it over to Molly, and then afterwards we can go back and address some other questions that people have.
Great. Okay.
This question, actually, if you'd like to pull up a website, you may on your screen. Question is, do you know of a source for eutrophication data for someone's local watershed?
Oh, it depends where it is. So, for example, let me. I'm going to put this back up and I'll tell you why in a second. So, if you are in the Chesapeake Bay region area, and in Maryland in particular, the Maryland DNR and the Eyes on the Bay, have a long-term monitoring program since 1984, and you can access those data online. Or if you can't manage to do that, they do have people who can help you do that. So that's one source of the data. And here, the reason I pulled this up is that the chlorophyll A and dissolved oxygen, they also have nutrient concentrations. So that's one source of data. Another source of data is your River Keeper Association, because there are just absolutely fabulous citizen monitoring networks that are in place and doing monitoring of the same kind of things that the state and federal agencies are doing. And so if you look in wherever you are, in your local watershed or River Keeper Association, they should be able to provide you data or send you to a place that can access data. And actually, you could sign up really to help to gather data too. I mean, it's really exciting. So that would be my answer to that, is the Eyes on the Bay, the Maryland DNR site, or look in your River Keeper or Watershed Association, because all of those groups do monitoring. So.
Thanks. You know what? And what I'll do is I will send Suzanne copies of everybody's questions so she can get back to you directly if it's relevant. If she's not into it this evening.
Because I think I talked a little bit too long. Sorry about that. But
no, it's absolutely fine. And we'll come back to some more questions, but I certainly want to get my colleague, my friend and colleague, Molly, on the line. Molly, your mic is hot and the screen is yours. So why don't we turn it over to you for the second half of our presentation, or the third half.
Okay. Thanks, Bruce, and thanks, Dr. Bricker. That was fantastic. I learned a lot. Hello, everybody. Thanks for joining us again tonight. In a very brief few minutes, I'm going to talk to you about how oysters in the Chesapeake Bay, the learning sequence, came to be. I'm going to give you a quick overview of the sequence, and then I'm going to share some resources that relate to topics in Dr. Bricker's presentation with you. As I said, Oysters in the Chesapeake is a kindergarten through 12th grade learning sequence, and it's based on concepts of three-dimensional learning. And for NOAA, it was the first of its kind to be developed. So why did 4 educators from NOAA decide to undertake this endeavor? And quite an endeavor it was. It was a few years ago, and the next generation science standards had just been released. And we, as an organization, a group of educators, wanted to learn how to use them to inform our future product development. We created lots of activities in the past and lesson plans, and we recognized that the need for a different kind of product as educators started to fill their toolboxes or file cabinets or online storage with three-dimensional learning resources. And why oysters, of all things? Well, all the things that NOAA does. We wanted something that was important to NOAA's work and relevant to a local audience. And we're located in Maryland, where besides the illustrious blue crab, many people do enjoy eating oysters. And tributaries of the bay had just been chosen as NOAA habitat focus areas for oyster restoration. So those two things came together at the right time. It took us about 3 years to produce Oysters in the Chesapeake for several reasons. While a couple of us had been classroom educators and we had understood the concept of 3D learning and had used it in theory, some in our classrooms, we had to understand how to navigate the NGSS. And the best practices about how to do that were still evolving. So we wrote and wrote and wrote again and wrote again, all without quitting our day jobs. And finally, we had a product that we were proud of that we released last year. Okay, the product is divided into 3 grade level bands, elementary, middle, and high school. Each one of these builds on the one before it. The activities progress from very simple in kindergarten, which I'll give you an example of, to more complex. They go from the role of oyster shells to in-depth activities using issues investigations in high school. The elementary sequence is more of a demonstration of what's possible with kindergarten to 5th graders and has 1 lesson per grade level. The activities in this section touch on the knowledge and the skills needed in later grades. The middle school section is separated into 2 modules, and I saw that the author of our middle school section, Peg Steffen, is on with us tonight. Good to quote, see you, Peg. The first module explores the changes in the physical characteristics of the Chesapeake Bay since 1608, when John Smith first sailed into the bay. And it moves on to investigations of water quality and investigations and research on land use factors that affect the bay. The second module explores the role of oysters in water quality, just as Dr. Bricker discussed, harvesting and oyster diseases and management strategies to improve the water quality and health of the bay. The high school section has 4 modules that explore more of the history of oyster-related issues. It also includes investigation of sustainable resource management, evaluation of habitat requirements for oysters, and research leading to stewardship actions for oysters in the bay, all at age-appropriate levels. Okay, so that was a down and dirty, real quick overview. Just going back for a second, I skipped over it. At the bottom of this slide is the URL for where you can find this. If you Google oysters in the Chesapeake Bay, it will be the 4th resource that you find. I did that just today to figure that out. Okay, here's a sample lesson from the elementary lessons. And this is kindergarten. And it's, as you can see from Dr. Bricker's presentation, this is a very complicated subject, can be very in-depth with many great minds working on it. If you're going to present it to kindergartners, you have to make it simple. The essential question that we used for this lesson was, what role do oysters play in cleaning the water of the Chesapeake Bay? The teachers and the students have a tub of water, and they add various items like food coloring, foam peanuts, pencil shavings, pieces of plastic bags, straws, all kinds of stuff, whatever they have handy, and they put it in the water. And then they talk about whether or not they would like to go swimming in that water. And I'm sure you will get lots of ooh and oh, I don't want to go in there. And so if you don't want to go in there, you talk about how to clean it up. They try different things like kitchen tongs or their hands, if they're brave, shovels, all those different things. And then the teacher brings out a filter. They pour the dirty water through the filter and talk about what happens, what they see, and how there are filters like this in nature. Next, the students get a tub of small items like little toys or something. They put in a couple spoonfuls of Cheerios and a cup of sand, and they have to design a filter to remove the Cheerios but leave everything else behind. So these kids aren't necessarily going to build this, but they can draw pictures of it and they can explain how their filter works. And this is the engineering part of this lesson. The lesson ends, with the teacher reading a picture book about oyster filtering, and the students draw a picture, and they can either tell or try to write a simple story about how oysters help clean the water. Now let's move on to middle school. Okay, it takes a watershed to raise an oyster. This is just one of the lessons in the modules. In this module, students are investigating watersheds and land use factors that influence water quality in the bay. Students look at data from a local watershed monitoring station and find the health of a waterway that's near them. I looked up, using the tool, the closest river to me, and that's the Anacostia River. And if you look on the bottom left-hand corner, you see the monitoring sites in and around the Chesapeake Bay. The report card that I used pops up, and it gave the Anacostia a grade of F, which, if you've ever seen the Anacostia, is not surprising. But the report card did have a positive, and that's very important when you're working with students, is to show them positive and not stick on the gloom and doom. And it helps to empower them to take action. So they can take the data from the report card and add it to their toolbox for use later in the module. Next, they use maps of the land use areas and parts of the bay and examine land use and compare it with local stream health. They learn about point and non-point source pollutants and determine local sources of that around them. I used the How's My Waterway tool by the EPA today, and I found out that the stream at the bottom of my street, which is Rock Creek, if any of you have been to or been around Washington, D.C., you know Rock Creek Park, and Rock Creek is a very important part of the area. It's a very important green space around here. And the Rock Creek has a lot of issues, but the tool also showed things that my neighbors and I can do to improve the quality of Rock Creek. Again, a positive spin. So students take all this information and they use it to consider the ways that pollution factors can be managed or reduced to improve water quality. By the end of the lesson, they develop a simple management plan of best practices to improve the Chesapeake Bay's water quality. I apologize for speaking so fast. I'm trying to use our time wisely. All right, here is a sample high school lesson from the module. So this lesson focuses on habitat requirements for oysters, including what they need to survive and what they need to reproduce in the Chesapeake Bay. The activities focus on biological as well as physical parameters. Students learn about the connection between the biotic and abiotic conditions in the Chesapeake and the effects of those on the eastern oyster. They analyze current water quality data from the Chesapeake Bay using the Chesapeake Bay Interpretive Buoy System, and one of those buoys is in the lower left-hand corner. And they compare that data with the oyster requirements at different life stages. And the life stage of the eastern oyster is top right image. Students also look at the habitat requirements for the eastern oyster, such as water temperature, dissolved oxygen, type of substrate they prefer, and the depth they prefer to grow in. They coalesce all this data and develop a picture of the best possible site for oyster restoration. Using that and the information available on the Oyster Decision Support Tool from NOAA, they identify 2 to 4 actual real-life sites in and around the bay where oysters can be restored. Each student chooses one final site and gives a presentation to the class about why that's the best place to start an oyster restoration project. As a culminating activity, the students choose the best restoration site from the presentations their peers gave, and they prepare a report for the secretary, the quote, Secretary of Natural Resources, where they describe the location of their choice and the reasoning behind their choice. Okay, that is a down and dirty overview of this resource. I encourage everybody to take a look at it. What I've shown you is just the tip of the iceberg, and there is a lot more in there that's fantastic to share with your students.
Thanks so much, Molly. So, Molly, how many units would you say there are within each one of those sections? The elementary, middle, and high.
Okay, so each grade level, well, the elementary has 6 lessons, and they're not so much units as individual lessons. To really be optimal for 3-dimensional learning, we would have a sequence for each grade level. For sake of time and resources, we weren't able to do that. So we chose topics where we could incorporate all aspects of 3-dimensional learning, including engineering. The middle school has 2 modules, and those each have several lessons. And then the high school has 2 modules, each with several lessons.
Oh, cool. Well, I know that I certainly have not even gotten through all the different sections. I am looking forward to it. I remember seeing it printed out once, and it was a huge tome of resources and materials. So it's really, I know that the materials are really accessible and they're really useful, particularly in making alignments to 3-dimensional learning. And I, for one, am so impressed at the work that was done in putting it together with yourself, with Peg, with our colleagues, Dale Glass, and others. So just a terrific shout out to all of you. You know, we are getting toward the end of the hour, so what I would like to do is I would like to actually go and review really quickly just one last slide, one or two last slides that I have, and then afterwards we can go back and we can take some additional questions if people want to stay on the line, which I really urge you to do. And thank you, Suzanne, for staying on the line as long as you are. But just yeah, some additional resources that I just wanted to share with you guys. was that NOAA's National Estuarine Research Reserve System is a terrific series of, I think it's 28 or 29 protected areas around the United States in estuarine environments that Suzanne was talking about. And they have an entire series of, I believe they're free teacher workshops that are field-based, and they're all around the country. They've got the schedule up now. I urge you to go and sort of take a look and see all of the wonderful resources that are there that you can take advantage of over the course of the summer. I also wanted to give a plug out to NOAA's National Centers for Coastal Ocean Science that I know Suzanne works very closely with.
Yeah, actually, I'm part of that group.
There you go. So you work very closely with them. And yeah, there are just many other resources and areas of interest and topics that focus on coastal resilience and focus on different kinds of research that are going on. So I urge you, if you are looking to check out some additional subjects, check out NOAA, or as we like to say, NCOS, the National Centers for Coastal Ocean Science. Lots of subjects for you. Also, if you want to learn a little bit more about oysters, I found these two sites through the NOAA Fisheries, Oyster Reef Habitat, and through NOAA's Chesapeake Bay Office, topic on oysters. This is pretty much everything you ever wanted to know about oysters, but were afraid to ask, or maybe you want to ask, but they're on those pages, so check them out. And really quickly, again, just as a reminder for some of you who have come in late, go check your email. I've sent everyone who's registered a link to our post-webinar poll. Please do it like right now, right after you're done with this webinar. It's really important for us to get these metrics, this information, and we do look at all the comments. And the only other closing thing I just want to talk about are our workshops again. We've got one, Changing Southwest Environment Trends and Challenges, June 11th through 13th in Flagstaff, Arizona. We've got, you can register to participate in that as well. We've also got environmental impacts to the Gulf Coast. What do we know? What can we do? That's going to be in Lamarck, Texas, which is in the Houston-Galveston area, June 25th through 28th. And also in July, the 21st through the 23rd, we've got Resilience Education Action, Our Place in a Changing World, which is going to be taking place in Oahu, Hawaii. And there's information for you to register there. And at this point, I just want to throw in my little closing moment of Zen slide of this is what a really beautiful estuarine area should look like. And hopefully, if you go to the National Estuarine Research Reserve site, sign up for a TOTE Teacher on the Estuary workshop, you can be in one of these magnificent, beautiful places. And I just want to take a moment to thank Dr. Bricker and to thank Molly for your presentations this evening. And I'm going to take a moment just to stop this recording, but we're going to continue to stay on the line and to continue to take questions. So for all of you who've come here this evening, thank you very much. Hope you have a wonderful evening and a wonderful summer as well. And we will see you soon.